Okay, so when we were looking at that expression before, and I said, hey, that looks pretty close to Gibbs. It's pretty close to Gibbs, but it's not exactly that state function. Let's talk about the Helmholtz energy. Okay, so we got to this expression. Right? Yeah, I organized it in a little bit weirder of a fashion. I want to get rid of the negative sign in front of du. I got to apply a negative sign. This becomes du. What does this become? Yep, minus t ds. And what happens to that inequality sign? Yep. So for a process to be spontaneous, what does the sign of this whole side have to be? Less than what? It has to be less than 0. It needs to be negative for the process to be spontaneous. We can represent this with a brand new state function. And we're going to give it the symbol A. And that's the Helmholtz energy. And A is defined as U minus TS. Oh, no, that's a different one. You're thinking angstrom symbol? Like that? That's like distance between atoms. So it is different. It's also a pain in the butt to find on like Word online. I don't know why. Need more chemists and that stuff. So what we're going to do, we're going to look at this under a couple different conditions. And we're going to see how we can apply it and how it connects to this thing. So you can see that part, right? How those two are connected to each other. Let's consider changing our conditions up. What is the change in A? At constant temperature. So let's start with this definition. Changes. When we're considering changes, what do we want to look at? If we want net impact, what do we got to do? In terms of like mathematical mumbo jumbo. So yeah, integrals. We need to do an integral if we want a delta, or yeah, that delta sign, right? Well, let's say we're looking at really, really small changes. What do we want to consider there? Not the delta, but what's the other symbol? Yeah, little d. So let's check out dA, and then we'll integrate it, and we'll figure out what is the total change. Okay, we're going to differentiate this guy. What happens there? Yeah, just du. Here we have two functions multiplied by one another. So what do we got to apply there? Right. Tell me, what are we going to get out of this thing? Yep, we can do S dt minus, what's the other one? Yep. And that's the overall change, right? Okay, can we make this simpler given our conditions? What do you, I saw the head nod. Yes, what is it? Oop, there's I gave it away. Yep. Because we have constant temperature. Okay, so now we're left over with dA is equal to du minus T ds. Now we want to get these out of small infinitesimal changes. We want net impacts. What would you do here? Yep. And what's it going to become? Not dA, but yep, delta A, change in the Helmholtz energy is equal to what? Yep. Minus T, yeah. Okay, you could show what would happen if we had an isentropic system where the entropy was not changing. Hint, hint. Might see that on Friday. However, what conditions besides constant temperature do we have here? Constant what? Yeah, volume. How valuable is that? Think about your experiments. How many times do you have constant volume? Almost never. This is important for condensed matter, like solids, or in some cases, like liquids under extreme pressures. You'd want to consider Helmholtz. However, what do we really want to look at? Constant what? Yeah. Okay. So constant volume is not favorable. In the lab. Constant pressure is, though. That's way easier. Okay, so let's return back to the Clausius inequality. How is this going to change at constant pressure? ds stays. What happens to dq? Yep. Little b. You've seen that a million times before. What is this? The heat exchange at constant pressure. It can be related to Cp. Yep, dH. It's enthalpy. Okay. When we look at this guy, what do we want to happen to entropy? Increase or decrease? Increase. When we consider enthalpy, do we want this process to be endo or exothermic? Yeah, we want it to be exothermic. And then the process will happen, right? What is that? Well, what state function haven't we talked about yet? Yeah, this is Gibbs. It's just in a different way of looking at it. Gibbs energy. Gibbs energy is defined as G, and then you can tell me the rest. It's what goes here. H minus, yeah. So question, you already know this one. You can spout it off to me from general chemistry and all your other classes, but I want to prove it. What is delta G at constant pressure? Oh, wait, I'm sorry, constant temperature. Derp. Okay, let's look at the small infinitesimal changes. dg, what's that going to be equal to? Yep, dh. Two functions multiplied together. What do we got to do there? Product rule. So what's this going to be? Yep. Yep. Okay, given our conditions, can we make this easier? We have constant what? So what's going to go away, Will? Yeah. dt is equal to 0. So that goes away. And we're left over with okay, we want them out of small infinitesimal changes. What do we want them in? Deltas, right? How do we get deltas out of this thing? Yep. And what are we left over with? Yep. Oops. And that's where that equation comes from that you use all the time. It's really talking about entropy. Okay. What we're going to do next is we're going to connect this and this to entropy. What we're going to show is a relationship between these things and how the entropy of the universe is increasing. Am I okay to erase this bit? Are there any questions about that? So given this equation, if we wanted to get rid of that negative sign, we'd have to switch this inequality, right? You get why delta G must be negative, or why we always talk about it being negative. I'm going to want you to be able to explain that on the next Quizlet, okay? All right, let's connect Gibbs energy and the second law. How are we doing on time? Okay, all right. I'm on time for once. There are many formulations of the second law. But another one we can introduce. Let's say I was going to consider the change in entropy of my surroundings. Oops. And the change in entropy of my system. And I wanted to compare that to delta S of the universe, the change in entropy of the universe. How would those things compare? Could be equal under reversible conditions. How often do we have truly reversible conditions? Never. So we'll put a little line here for an inequality. What should be larger? The change in entropy of the universe or the change in entropy of these two things? Yeah. So which way should the carrot's mouth point? Yeah. I was told it was a little Pac-Man, but I don't think anybody plays Pac-Man anymore. So my grandfather used to take me to the Burton, like when he would babysit me, and he would let me play Pac-Man while he would drink and smoke. Very different lifestyles now. Okay, but what's the minimal case? What's the best case scenario? I think, Serena, you said it earlier. Yeah. Well, let's consider the minimal case. Delta S, a universe. And I'm just going to shorten it to uni S surroundings system, so we don't have to rewrite it a lot of times. Okay. We're going to jump back to the Clausius inequality again. Oops. You can show that delta S of the surroundings is equal to delta H of system divided by T. That negative sign, where does the negative sign come from? What are we relating here? The surroundings to what? System. So if the system gains heat, what happens to the surroundings? Yep, and what happens if the system loses heat? Yeah, so this negative sign just comes from the relationship between the two. That feel comfortable? Okay, so let's take this and plug that into our expression over here. Delta S, a universe, is equal to, what's going to be the next term? T plus delta S system, right? Again, we hate things in the denominator. What would you suggest to do to this thing? Yeah, multiply by T. So we get T times delta S of universe is equal to negative H system plus T delta S of system. What do you not like about that expression right now? Personally, I don't like the negative in front of the delta H. So what would you do with that? Yeah, multiply by a negative. You get negative T delta S universe is equal to delta H of the system minus T delta S of the system. What's this thing? Yeah, that's delta G. So delta G, what's delta G equal to from this equation? So really, when you measure changes in Gibbs free energy, what is it proportional to? The change in entropy of the universe. When you make that observation and you measure delta G, you're really telling something about the entire universe, which is crazy to think about that. Like, I can measure this wheel moving around and I'm getting a ton of information about the entire universe. Crazy. We're all connected. Everything's connected. It's all energy, man. So really, negative sign. Why do we want delta G to be less than 0, right? For the process to be spontaneous. What do we want to happen to delta S of the universe? To make sure a process is spontaneous. Yeah, it must be greater than 0. Because of this negative t here, that's why you want delta G to be less than 0, because you want the entropy of the universe to be increasing. Okay. All right, and from that you can really tell if a process will or won't happen. Every single process. You can't tell how long it will take, but you can tell if it will or won't, given an infinite time scale. I think is pretty cool. Okay. Are there any questions about that? Okay. What I want you to be able to do for your Quizlet is to take these definitions, know those. What's the Helmholtz one? Yeah. And apply different conditions to them. Also, use the Clausius inequality to figure out those things. And then I might ask you some questions relating to different conditions associated with this and calculating changes. Are there any other questions that you guys might have?